The problem we're trying to work out as a group is figuring out whether or not dogs like Lassie and Elvis are able to optimize the time it might take to fetch a ball from a body of water or rescue someone who might be drowning in that water. The different data sets will allow us to evaluate whether dogs have the natural ability to optimize the time needed to go from point A to point B and how they're doing it. In order to solve our problem, we were proposed with a few situations that might help us come to a conclusion. Using an equation created from the following diagram, we were able to find how far Lassie should run on the beach before actually getting in the water and swimming diagonally to a drowning person to save them. Here we have T of Y, and it represents the time it will take to get to the person that's drowning. R will represent the rate that Lassie is running. S will be used to represent the rate that Lassie is swimming. X, Y, and Z are going to be correspondence to the graph that we were shown before. And in the equation, square root of x squared plus y squared will represent the distance that the dog will swim in the water, while z minus y will stand for how far Lassie is going to be running on the beach. We'll use our knowledge of distance and time and rate to find the amount of time it'll take to get Lassie to the drowning person. Since we know that distance equals rate times time, we also know that time equals distance over rate, and that's the equation we'll be using. Using the time formula, we've established that the time Lassie runs along the beach is represented by z minus y divided by r, and the time it will take her to swim in the water is represented by square root of x squared plus y squared all over s. In the diagram that we were given, z and x were constant distances, so that means the only variable that can be changed to minimize the time needed for Lassie to reach the person is y. To find the minimum distance for y, we needed to find the derivative of our initial equation and set it equal to 0. The final equation we will get will be what we need to find what distance for y will minimize the time it takes for Lassie to reach the drowning person. We found that the derivative of t of y is y over s times the square root of x squared plus y squared minus 1 over r. After finding the derivative, we set it to 0 and came out with the equation y equals s times x divided by the square root of negative s squared plus r squared. The equation shows that the distance that Lassie should run on the beach actually depends on how far into the water the victim is. In addition to the vertical distance, Lassie's running and swimming speeds also play a factor into how long it will take her to reach the victim. One catch of the equation is that Lassie's running rate has to be faster than her swimming rate. If her running rate and her swimming rate are equal, we would end up with the square root of 0 in the denominator, and that would lead to an inconclusive number. If her running rate is less than her swimming rate, then we would end up with the square root of a negative number in the denominator, and that would lead to a negative root number or imaginary number for distance, and that wouldn't give us an answer either. In essence, her running rate must always be faster than her swimming rate, so we could calculate the distance she would need to go down the beach so that she could reach the victim at a minimum amount of time. In another study we were given, we have data on a dog named Elvis. The owner clocked Elvis's times while catching a tennis ball on a beach and swimming. From that, we have this data table. Using the data from the table, we were able to calculate the average running time for 20 meters and the average swimming time for 10 meters. Then, we found the average running and swimming times in meters per second. The average running time will serve as R and the average swimming time will serve as S in the equation we found in part 1. With this data set, we will be able to analyze the relationship between the distance of y and x that will help us figure out if dogs have the natural ability to optimize things. Using the derivative t prime of y that we found in part 1, we inserted the values of r and s into the equation and came out with our final product before setting the equation to 0. The equation is t prime of y equals 1.1468y divided by square root of x squared plus y squared minus 0.1575. With the equation we were left with, we set it to 0 and calculated an equation that defined the relationship between y and x. This equation means that in order for the time it takes Lassie to reach the person to be minimized, Lassie should run almost to the end of the beach and then jump into the water so that y is 0.139, the distance of x. This was expected because the running rate, which is r, is significantly greater than the swimming rate, which is s. Therefore, if Lassie runs and swims at about the same rate as Elvis, then the equation y equals 0.139x should minimize the time it takes for Lassie to reach the drowning person. This set of data points was taken from Timothy Pennington's, the owner of the dog Elvis, Lake Michigan experiment done with his dog. We intended to use the data points that correspond to the distance from the ball to the shore, which is the points found in the X column, and the distance, which are the points found in the Y column, to see if Elvis had the ability to actually do calculus. Using the data points that Pennington collected, we plotted them and configured the graph below. The graph shows the optimal relationship between distance y and x. The line found on the graph shows the relationship between y and x that will evidently optimize the time, which is what we found earlier, y equals 1.39x. Obviously, the points on the graph are Pennington's data he collected with his dog Elvis, but as seen on the graph, it's clear that the points fall very close to the y equals 1.39x line. From the graph, we can see that the points are the closest to the line when x is less than 10. And at about the 15-meter mark, the data points start to fall further and further away from the line. From all the data we were given and the models we've created, we can finally say that dogs like Lassie and Elvis do have the ability to optimize the time it takes to see something in the water and go and get it. Whether it be a drowning person in Lassie's case or a tennis ball in Elvis's case, from the graph we configured from the points taken from Timothy Pennington's experiment, we were able to conclude that the dogs are especially capable of optimizing time when something or someone is 10 meters or less away from the shore. It's important that the object or person is also vertically away from the shore because the dogs don't necessarily use any type of measurement, but it may in fact just be using their eyes to gauge the distance. The dog's ability to assess longer distances isn't as good as their ability to assess shorter distances, but that doesn't mean that they aren't able to do both. One is simply more accurate than the other. We can't necessarily say that the dogs are doing calculus, but we can say that they have some kind of ability in them to see something in the water and figure out the quickest way to get to it. All in all, it is verifiable for us to say that the dogs are capable of optimizing the time it takes to go and get something from the water if need be. Looking at the conclusions we were able to come to, we've realized that our answers are extremely plausible. Dogs have always been said to have a sense that most people will never understand, and we've seen that come through time and time again. In order to get through this project in a timely manner, we all decided that it would be easier to complete all the data and work through it as a group. It would have been harder for us to do each part individually, so instead we worked gradually. Our use of derivatives allowed us to ultimately come down to an equation that could not only measure the relationship between y and x distances, but also serve as a baseline of how accurate a dog's ability to optimize can be. Before we began looking through the experiment, we hypothesized that the dogs would be able to optimize the time it would take to go and retrieve something, and after completing the project, we can say that based on our data, we were right.